Hello, my name is Dominic Clevey. I'm a professor at Central Washington University. I'm here to talk today about logarithms. We are introducing logarithms today, and we're going to start a long time ago, almost 400 years ago. In 1614, Henry Briggs, he was the first professor of geometry at Gresham College. At the time, 1614, he was one of the leading mathematicians in all of England, maybe the leading mathematician in England. He went one day to the library and saw a book he had never seen before. A book written by a Scotsman named John Napier. Napier was, and I now quote from James Glick, the 8th Laird of Merchiston Castle, a theologian, a well-known astrologer, and a hobbyist of mathematics. He did it in his spare time because he thought it was fun. He wrote a book which rocked Briggs' world. He'd never seen something like this. It was full of high-tech developments, of new innovations, of beautiful ideas, the likes of which he'd never seen. Henry Briggs was so excited he traveled all the way to Scotland just to meet this man, this John Napier. At their first meeting, he reported later, they began with a quarter hour of silence, spent beholding each other in silent admiration before one word was spoken. Briggs goes on. He broke the trance, saying, "My lord, I have undertaken this long journey purposely to see your person and to know by what engine of wit or ingenuity you first came to think of this most excellent help unto astronomy. Namely, what? What is it you know because you heard the introduction, but pretend you don't? What is the marvelous new idea that was introduced here at the time, the biggest, most exciting advance in mathematics in 2,000 years? It was the logarithm. Logarithms are where we're going today. If you've seen them before, it's possible you don't like them. Students are sometimes scared of logarithms, but you needn't be. They are not difficult. They are incredibly exciting. They are incredibly powerful, and you should think of this as a high-tech tool to process information, the likes of which cannot be done any other way. All right, you ready? Logarithms. What are they, and what are they good for? The basic idea comes from another idea in mathematics, and it's an idea that says mathematicians always want to be able to undo whatever it is they do. You see, we make mistakes a lot, mathematicians. We want to be able to go backwards. Computers are good at undoing. There's in fact an undo command on every keyboard. There's an undo command on my screen right here. Mathematically, we want to be able to do the same thing again. Let's say I have some way of making a variable y. Let's say I want to find y by taking x and adding 3 to it. Y is x plus 3. If after this I want to find x again, how do we find x? If I give you y, what do you do to find x? Well, it's pretty simple, right? You've been doing this since the first grade. If you added 3 to get y, you have to subtract 3 to get x again. And so x is simply y minus 3. Alright, this is the first grade version of what we're talking about, the first grade version of undoing what we've done before. How about the 4th grade version? By 4th grade, we're really good at multiplying. What if y is 3 times x? Now, if I give you x, how do you find y? How do we undo what we've done? Well, again, it's simple, right? You've been to 4th grade. We know if we want to find x again, we just take y and divide it by 3. You'll pardon, I hope, my handwriting. That's supposed to be a 3. Alright, let's move on. What else could we do? What else might be tricky? Well, what if we try exponents? If I tell you that y is equal to x cubed, now if I give you y and you want to find x, what do we do? A little bit harder, perhaps not a 4th grade problem, but what do we do if we want to find x? X is equal to what? Well, I take y. If I cubed x to get y, then I take the cube root of x to get it back again. If y is x cubed, then x is the cube root of y. Again, so far, not too complicated. Again, these are things that you know. There's really only one combination of basic operations left that we haven't used. What if instead we write y is 3 to the power of x? Now, if I give you y, how do we find x again? Here, if you have x, it's easy to find y, but how do we go backwards? What is this magic thing that will undo exponentiation? And it's the same thing that was magic back in 1614. It's the same thing that sent Henry Briggs running across the sea to Scotland to find John Napier. The answer is a logarithm. Here we have that x is equal to the logarithm. In fact, we'll call it the base 3 logarithm of y. Logarithms undo exponents. This is a big idea. This is what we need to use. And in fact, this last idea, this last row, is such a powerful thing. We're going to write it again. We're going to write it again inside of a box. And if something's inside of a box on a mathematics lecture, you know it's important. And certainly this is. So this will be our big definition. And let's see. If you remember only one thing from today's lecture, this is the one thing you'll need to know, that if you see y is equal to the log base b, what's b doing here? We'll come back to that in a minute. Log base b of x. This means exactly that x is equal to b to the power of y. Take a second to put that partly into your brain. We'll come right back to it. What is this letter b? Remember what we had a little bit ago? If we have an exponential equation, look at this thing on the bottom, this y equals 3 to the power of x. The 3 here is the base of our exponential expression. Whenever you see something raised to a power, we call the bottom thing the base, we call the top thing the exponent. 3 is the base, and 3 is also the base in the logarithm. These have to be the same thing, they have to work together, so 3 has to be doing sort of the same thing in both places. 3 is the base. And what letter should be used for base? Well, b. B is a great letter for base. So if we have x equals b to the y, that's exactly the same thing as y is the base b log of x. I'll say again, this is the single most important thing you need to know for logarithms. In fact, if you're fairly clever at doing mathematics and you remember nothing else but that equation, you might be able to pass your quizzes. You can use it to do as much as you want. There are small tricks. We're going to learn the tricks, but that one idea is the big idea. It's so big, in fact, we need to practice it more right now. Let's look at it one more time. If you see y equals the base b log of x, that means x equals b to the power of y. So let's practice. How do we practice this? Well, let's practice translating exponential equations into logarithmic equations. So we're going to have here, maybe in fact we'll start with a blank screen. If I write the exponential form of an equation, what we need to be able to do is turn it into a logarithmic form. And to take the exponential form of an equation, take one that we know. Can you think of any equation involving exponents that you know well? Here's perhaps an easy one. How about 10 squared equals 100? Can we turn this into a log equation? Can we write the same thing in our new language? Well, we could review what's going on here. Can we look at the equation and see the same thing? I will tell you, for those of you who are visual learners, who want to picture what's going on, if you start with an equation like x equals b to the y, what happens when it becomes a logarithmic equation? The x here is by itself, so it gets a log in front of it. You can almost picture the b, the base, swooping over to the side of the equation to become the base of the logarithm. And when it does, the y falls down. Can you see it here? The log before the x, the b which is snuck in underneath it, and the y which is tumbled down to its new place. If you want to picture this as a movie, it might be good. If you don't like this sort of thing, ignore it and memorize this. Find some way for this to make sense. Let's then go back. If 10 to the power of 2 is 100, what happens? Well, we're going to take the log of 100. Log base what? What is the base of the log? What is this little number written next to the log? It's the base of the exponent, right? It is the base of what we had over here. The 2 falls down. 2, therefore, is the base 10 log of 100. Let's try it again faster. If 10 cubed is 1,000, and I hope everybody believes that in fact 10 to the power of 3 is 1,000, then what? Then 3 is the base 10 log of 1,000. At this point, you may be able to see what question is being answered by logarithm. If you see the base 10 log of 100, what does that mean? What is the base 10 log of 100? You see the base 10 log of 100, what that means is 10 to what power is 100? Could you answer that question? Could you have answered that question 20 minutes ago if someone has talked to you in the hallway? Quick, I need to raise 10 to the power of something to get 100. What should that something be? 2, right? 10 to the 2 is 100. Of course you know this already. 10 to the 2 is 100. And that's exactly what we're saying over here. When we have base 10 log of 100 is equal to 2. 2 is a thing, we raise it to the power of. Let's try one more. I could write 2, let's see if I can make that look a little bit better. 2 to the power of 3 is equal to what? Well, 2 times 2 times 2 equals 8, I think we all know. If 2 to the power of 3 equals 8, what does that mean? Well, that means 3 is the base 2 log of 8. If you can write any equation down in exponential form, you can turn it into a logarithmic equation. And I will say it for, I think, the 4th time so far. Please, please believe this to be true. This is the single most important thing you need to know. In fact, it's so important, may I urge you right now to reach out and pause your DVD player. Write down 4 exponential equations. Maybe you know that 5 to the 5th power is 125. Maybe you know that 2 to the 20th power is 1,048,576. Or maybe you want to pick something easier. Write down 4 exponential equations and try to turn them into logarithmic equations now. The time you spend doing this will pay off handsomely soon. I'm going to assume you've all done that and that you're back. Welcome back. Let's now move forward and think about what else we can do with logarithms, because we did something sneaky. We did something a little bit underhanded that perhaps we should make more clear. What did we do? Well, when we wrote something like the base b log of x, we said we know a way to interpret that. That says b to what power is x? The log answers that question. But what do you think of when you think of x? X is usually a variable. X is allowed to change. X is allowed to vary in different ways. And so, in fact, this thing, this base b log of x, is a function. I'm told if I write on the whiteboard over here, it might not show up very well, but let's try it just once in really big letters. Just once to see what we're talking about. The base b log of x. The base b log of x says that b to some power equals x. If x changes, this is a function. This is something that you can graph. This is something you can manipulate in all the ways that you always manipulate functions. And this idea is a powerful one. The idea of taking a mathematical operation and turning it into a function is not at all obvious. In fact, John Napier, who invented logarithms, Henry Briggs, who first discovered them with Napier's help, who brought them to England, it never occurred to these people to do this. Taking an object like logarithm, like sine, like cosine, like square root, and turning it into a function is a profound idea, which was not done in mathematics until about 1750. It was Leonard Euler in his Introductio in Analysis Infinitorum who finally had this wonderful idea of taking sine and cosine and square root and logarithm and making functions out of it. If you don't like functions, this is probably not exciting to you. Couldn't he have left well enough alone? Do we need functions? It turns out they're way easier than the old way of doing it. Math used to be far harder than it is. We can be grateful this is here. So this is a function. It's a wonderful thing. Be grateful for it, for my sake. Please. If it's a function, what can we do with it? We can graph it. Let's try this. What is